Okay, so in this section, we're going to put into practice now what we learned from the previous two sections, and we're going to tie those together in what's known as nomenclature. So in chemistry, nomenclature is just a big fancy word that just means going back and forth between the name and the formula. And in this case, of our ionic compounds. All right, so we've seen how to come up with the formulas of our ionic compounds in the previous section. Now we're going to take a look at how we name our ionic compounds. So when you name an ionic compound, we're going to name it as it's written. Okay, and what that means is the metal goes first. So the metal ion is first, and then the non-metal is second. Okay, and then as we'll see in the subsequent sections, we can make a more general statement when it comes to nomenclature. We can say that cation goes first, the positively charged thing goes first, and then the anion goes second. All right, and we saw before that metals tend to form cations, non-metals tend to form anions. All right, and this is the order in which we write the formulas for the ionic compound to begin with. All right, so let's take a look here at an example. We'll just use a couple that we've seen before. So we have Na and we have Cl. All right, so the metal here is Na, which is sodium. So that goes first in the name. And then Cl is not chlorine, right? In an ionic compound, it's the Cl minus ion that we have, which is not called chlorine, it's called chloride. Right, so it's got that IDE ending. So NaCl is sodium chloride. Similarly, we saw in the previous section, we had MgO. All right, so the first name for this then would be magnesium. It's just the name of the metal. And then oxygen as a last name is not oxygen, it is oxide. All right, so if we take a look at some other ones down here, for instance, Al2O3, we have our aluminum as a first name, that's Al, and then oxygen as a last name would be oxide. All right, let's take a look at another example. Let's do B in this one. So we have Al2S3. All right, so when we name it, the metal goes first, and the metal is going to be the first thing in the formula. So the first name for this here would be aluminum, or aluminium if you want to pronounce it that way. And then sulfur as a last name is not sulfur, it is sulfide. All right, so aluminum sulfide will be the full name for that ionic compound. Let's take a look at another slightly different way to approach this. Here we have some combinations of compounds or ions, for example. What we're going to do is put them together in the right ratio, and then we're going to name them. All right, so let's do, we won't do all of these. Let's do this one right here. So we're combining aluminum and the sulfide. All right, so when we write the formula, metal goes first, non-metal second. So then we can do our cross charge. The 3 on the aluminum becomes a subscript on the sulfur, and then the 2 on the sulfur becomes a subscript on the aluminum. So we have Al2S3, and the first name for this then would be aluminum, and then sulfur as a last name would be sulfide. All right, so that'll be the name for that ionic compound. All right, so that was the one that we actually saw previously. Let's do another one here. The upper right corner, so we have Na, sodium, and N3 minus. So the metal goes first, non-metal second. The 3 on the nitrogen becomes a subscript on the sodium, and then the 1 here, which is understood on the sodium, becomes a subscript on the nitrogen. So Na3 N1, or just simply Na3N, would be the formula. The first name for this, Na, is sodium, and then nitrogen as a last name is nitride. So it's sodium nitride. So far we've been looking at metals, for instance, that have a fixed charge. Right, and these were the representative metals that we saw. And we were able to predict their charges based on their group number, right? The charge was equal to the group number. However, we're going to also run into a slight exception to that rule. We're going to encounter metals that can have variable charges. All right, and the majority of these metals are known as transition metals, and because the majority of these metals actually reside in that central block of the periodic table. So the majority of these these transition metals can actually form different charges, and we call these type 2 cations. And the previous example that we looked at, the fixed charge metals, we call those type 1 cations. So these special types of metals that can have different charges, we find them mostly in the transition element area of the periodic table. And what's special about them is that they can form different charges. So for example, copper can form +2, or it can form a +1 charge. Iron can be +2, or it can be +3. Chromium, for example, can be +2 or +3. Lead can be +2 or +4. So how do we know? How do we represent which charge it is that we're dealing with? Well, what we're going to use is we're going to use Roman numerals to specify the charge. Right, and we only use the Roman numerals for these special types of metals known as the transition metals or the type 2 cations. You wouldn't want to use it, for example, for sodium, because sodium always forms a +1 because it's in group 1. Right, these you find them in the transition area, and we don't know what their charges are. We're going to have to figure it out. So if you don't remember what Roman numerals are, I'll just remind you here really quick. So the Roman numeral for 1 is I, and we're going to put it in parentheses. The Roman numeral for 2 is II. Roman numeral for 3 is III. 4 is IV. 5 is 6. I'm sorry, 5 is V, and then 6 is VI. For the Roman numerals, those are the most common ones that we'll encounter. It's not that you can't have 7 or 8, for instance. You can, but these are going to be the most common ones that we're going to see. Right, and we put them in parentheses. So we're going to use these Roman numerals as part of the naming or the nomenclature of these metals that can have variable charges. So here's maybe a much longer list of metals that can form different charges. So let's take a look at how we determine the charge on a metal that belongs to this category. All right, so we'll take a look here at Mn F2, and I'll kind of walk you through how this works. All right, so if we have to name this, all right, as we've named it before, the metal goes first. So Mn is not magnesium, it's manganese. And then F here, that's fluorine, and as a last name, fluorine is fluoride. What you need to notice is that Mn, manganese, is a transition metal. All right, so we're going to need Roman numerals to tell us what the charge on the manganese is. So we don't know what the charge on the manganese is, but we do know what the charge on the fluoride is, right? F is always -1 because it's in group 7. From the formula, we have 2 of these, right? So that gives a total negative charge in this compound of -2. And remember, your ionic compounds have to be neutral, always. So something then has to cancel this out. So the charge on Mn must cancel out -2. So then the charge on the manganese then has to be +2. Right, so we can determine the charge by doing a little bit of math, and then we can put the Roman numeral for 2 in our name, right? So that's manganese 2 fluoride. This table from your textbook kind of shows you the most common elements or metals that can form variable charges. So when you look in here, you'll see the vast majority of them are going to be in the transition block. But what you'll also see is that there are a couple that actually reside out of that area, right? So for instance, tin and lead and bismuth also belong to that category. But we see those a little less commonly. So when it comes to your nomenclature, all right, you want to make sure that you pay attention to the to see whether or not you have a transition metal in the formula. In that case, you need to include the charge in the name by using the Roman numeral. So let's take a look at an example. And we'll actually use a couple different examples to illustrate this. Right, so the two examples we'll use here, FeO and then Fe2O3. So let's just go ahead and write the first name for each of these. So Fe, as you may know by now, this is iron. And then Fe2O3 also has Fe as a metal, so this is also going to be iron. When you look on the periodic table, right, you'll see iron is smack dab in the middle of the transition block, right? So that means it's going to have a variable charge. So we would need to include, reserve some Roman numerals for our name. And then oxygen as a last name is oxide. And we have oxygen as a last name for both of these. All right, so if you name something and you say iron oxide, well, which is it? Is it the one on the left side, or is it the one on the right? Because you're not specifying which one, right? And as you can see, they're different compounds. So we need to say then what the charge on the iron is in each of these compounds. So we don't know what the charge on the Fe is, but we do know that oxide, right, is always 2-. And for this first one here on the left to be overall neutral, the iron has to be +2 to cancel that out, right? The +2 and the -2 must cancel. So because the charge on the iron here is +2, this is iron 2 oxide. All right, another way to look at it is we can say the charge on the iron plus the charge on the oxygen should equal to 0. All right, and then we know what the charge on the oxygen is. It's -2. So then we can do a little bit of math. Then we can say iron is equal to 0 plus 2. So iron is equal to +2. Right, and that's the charge that we get here. So you can do it, mathematically, do a little bit of algebra, or you can, in this case, you can look at it and you can kind of tell relatively quickly. So let's take a look at the one on the right. All right, so we said that the charge on oxygen is, the oxide ion is always -2. But how many oxides do we have? Well, we actually have 3 of these, right? So that gives -6 for the oxygens. So whatever the charge on both of those irons are, so 2 irons plus the charge on the oxygen, which is -6, should overall be neutral or be equal to 0. So if I take my 2 irons now, because I have 2 of them in my formula, I can move that -6 to the other side. So both irons then have to equal +6, which means 1 iron has to equal +3. So we take that +3 and we stick it in here as a Roman numeral, and this ends up being iron 3 oxide for the name for this particular compound. All right, so iron 2 oxide versus iron 3 oxide. Obviously the names are different and the chemical formulas are different as well. All right, so this is one case where you're going to run into or another layer, I guess, in your nomenclature when it comes to your ionic compounds. You have to pay attention to whether or not you have one of these metals that can form variable charges. All right, so let's take a look at how we can go in the other direction. Let's say we're given the name and we have to come up with the formula. All right, so we have here tin 2 chloride. So let's break this down. The symbol for tin is Sn. And chloride, as you know by now, that comes from chlorine, Cl. So what are the charges of these things in this ionic compound? Well, chloride, because chlorine is in group 7, is going to have a charge of -1 always. And from your name here, right, the tin 2, this actually tells you the charge on the tin ion is +2. All right, so you're actually told in the name what the charge on the metal ion is. So when we combine these then, all right, we can do our cross-charge thing. The 1 on the chloride becomes a subscript on the tin, and then the 2 on the tin becomes a subscript on the Cl. So we end up with SnCl2 as the formula for tin 2 chloride. All right, so going back and forth from the name to the formula, and from the formula to the name, that in essence is what nomenclature involves in chemistry. And that's the nomenclature for your basic or your very fundamental ionic compounds. All right, and because these compounds were looking at ionic compounds made up of just 2 types of ions, we call these binary ionic compounds. Right, because they're made up of 2 types of ions. Right, in the next section, we'll take a look at some other types of ionic compounds.